In this video, we're going to generalize what we did in the previous one, where we projected onto just one line or onto a vector. Now we're going to project onto a subspace. So let's look at our setting. Well, let's take some vectors a1, a2, all the way to an. And let's say that those vectors have m components. Now, when we look at the span of these vectors, or all linear combinations of these vectors, we know that they represent a subspace in Rm. For the sake of making certain things a little bit simpler, let's assume that these vectors are linearly independent and therefore they give us a basis. So assume a1, a2 through an are linearly independent. Of course, if we have an algorithm, if we're given some vectors with specific numbers, we can always discard some vectors to have a linearly independent set, and we already talked about algorithms for that. Namely, we put these vectors into a matrix, reduce the matrix, regardless of whether we represented them as rows or as columns. All the rows or columns, depending on our representation, that don't have pivots can be discarded, and all the other ones can be maintained or preserved, and they will give us a basis for the same space. So span of a1, a2, an, so the set of all linear combinations of these vectors, that's what span means, is a subspace of Rm. So implicitly, we are assuming that n is less than or equal to m. But let me just say less here, because otherwise we don't have a subspace, we have the whole space. So let's assume that this subspace is really non-trivial. It's smaller than the whole thing. So now the question will be, if we take a vector b, so take a vector b in the space Rm, we want to find the projection P, so the projection P onto this vector space. How do we know that we can do this? Well, the trick is very simple. If you look at A, we want to use the fundamental theorem of linear algebra, of course. So if I define the matrix A to be the matrix whose columns are these vectors, A1, A2, all the way to an. Now remember, these vectors being in Rm means they have m components. There are n of them, so this matrix A is of size m by n. Now all of a sudden, this vector space we're talking about is just the column space of A. So we know that we can find an orthogonal projection onto the column space of A, and the error will be in the left null space, because we have the second part of the picture that represents the fundamental theorem of linear algebra. So here we have the column space of A, and we know that its orthogonal complement is the left null space. So these are orthogonal complements. So what we are saying is we are in Rm, we're taking some vector B. In general, we want to find, so we know from the theorem that B can be represented as a part P in the column space and the part E in the left null space. So this is how we're actually trying to decompose the vector B into its components P and E, where P is in the column space of A and E is in the left null space of A. So this is what we're going to be talking about here, how to find P, right? That's the whole point. Of course, I could say how to find E. It's kind of the same question, because once you find one, you find the other, but we'll talk about finding P because that's where we have our methods. But ultimately, the question is how to find P. Now, P is in the column space of A. So we know that P is in the column space of A. Okay, that's the whole point. We're trying to find a P that is in the column space of A. Now, if it is in the column space of A, then P is of the form A times some x hat, right? So the x hat will become more clear tomorrow why I'm using a hat and not just x. So bear with me. Think of it as hinting towards projections. So because P is in the column space of A, we know that P must be of the form AX hat for some x hat, right? We're not trying to solve this equation. We are saying that there is an x hat so that P equals A times x hat. So the goal is to find this x hat. Now, we know if that is P, what is E? Just again from this equation, B equals P plus E, we know that E is B minus P, which is A times x hat. And because E is in the left null space of A, we know that E and P are orthogonal, right? E is orthogonal to P. I could say E is orthogonal to the columns of A as well, right? I could say E is orthogonal to the columns of A, right? That's what that means. It's orthogonal. When we say that a vector is orthogonal to another space, what that means is that E is orthogonal to every vector in a basis for that space. And since we're talking about the column space of A, we might as well say it is orthogonal to the columns of A. So we have the following. We have that the error term is B minus the projection, which is actually A times x hat. And we know that every column of A is orthogonal to this vector. So that means that A1 transpose times B minus AX hat must be 0. So this vector E is orthogonal to the first column of A. It is also orthogonal to the second column of A, all the way to the nth one. So all the columns of A must be orthogonal to what is in the left null space, to this error term. Well, I can represent this system of equations via matrix multiplication in the following way. I can put all these A1 through AN as the rows of a matrix. They are row vectors because of the transpose. Multiplying. So B is a column vector. AX also gives us a column vector. So this B minus AX needs to be a column vector, which I'm going to represent like this. Right, that's a column vector. And I need this to be 0. That 0, what I mean by 0 is a 0 column, but I'm not going to write a column. Question is, what is this matrix? Well, this matrix is nothing more than A transpose. So you see, we have A transpose times B minus AX hat is 0. And this is that key equation. Now, when I open parentheses here, so another thing. Now, just from this form, you see that this vector needs to be in the null space of A transpose, or the left null space of A. So this equation is consistent with the picture that we have over here. We're looking for E in the left null space of A. So I could have just said straight away, A transpose E needs to be 0 because E is in the left null space of A. So that's what that means. So perhaps we took the long way to come to that conclusion. And the reason for that is we were saying that the two spaces are mutually orthogonal. Now, this is just while I present the theory. Of course, you will always start right there. Now, this equation has a more famous form. So here's the normal form. Statistics books, anywhere where least squares approximations are defined, you are going to see the following form. A transpose AX hat equals A transpose B. So this is the normal form of the equation. So once we have that equation set up, then we know how to find X hat. Namely, you can compute A transpose B. This is going to give us a vector. You can compute A transpose A, that's a new matrix, and then solve that system. You have a new matrix times X hat equals some vector, where so we can solve that just as a system of linear equations, a matrix of the form AX equals B, where you know that there is a solution. You're guaranteed to have a solution. Now, because we took the columns of A to be linearly independent, it follows that this matrix is actually invertible. We will prove that in a minute, but the conclusion is, since the columns of A are linearly independent, A transpose A is invertible. If we don't take the columns of A to be linearly independent, then there is nowhere else to go from this equation. That means A transpose A will not be invertible, and it will mean that this system has infinitely many solutions X hat. But if we take only pivot columns in A, then A transpose A is invertible, which means that this system has a unique solution. So to make our lives easier, we are going to choose to project only onto a basis. We're not going to be using linearly dependent vectors when we can help it. So if A transpose A is invertible, then I can multiply by the inverse on both sides of the equation. And what I'm going to get is X hat equals A transpose A inverse. I can't split this. I can't say A inverse times A transpose inverse. A is usually a rectangular matrix, so A inverse might not exist. We can't assume that it does exist, but A transpose A is a square matrix and it is invertible. Therefore, I can write A transpose A inverse, which means I first have to calculate what is A transpose A and then find its inverse, and then multiply by A transpose B. So this is that vector X hat which defines the projection. Now from here, if you recall, the projection was given by AX hat. So I just multiply by A and I get A times A transpose A inverse A transpose B. And this is quite similar to what we had in the one-dimensional case. If you recall, when we were projecting onto one line, the projection looked like this. It was A transpose over A transpose A. Well, by putting A transpose A in the denominator, that's the same as taking the inverse for A transpose A. And because in the one-dimensional case I have a number, I could very well put it in the middle. But when you talk about matrices, you have to respect the order. You cannot switch things around. And I'm just trying to point out that this expression is consistent with this expression. So if you take A to only be one column vector, then you can rewrite this matrix as that matrix. I am missing a B here. So we said this was the projection matrix in the one-dimensional setting. Nothing has changed here. The projection matrix is A times A transpose A inverse times A transpose. So when we apply this matrix onto another vector in Rm, we are going to get the projection of that vector onto the column space of A. All right, this is the entire theory. These are the equations. There is nothing more. So tomorrow we will see that this x hat, so I'm going a little bit ahead, but this x hat will be the least squares solution. We'll revisit this tomorrow. This P is the projection of B onto the column space of A, and this capital P is the projection matrix onto the column space of A. Let's look at an example. Let's solve some numbers here. So here is example 2. If A equals 1, 1, 1, 0, 1, 2, and B is the vector 6, 0, 0, find x hat, the projection P, and the projection matrix capital P. So what do I want? I want these formulas, right? And why don't I just copy them and take them along? We don't have to memorize things. Oops. So here are the formulas. I am going to make them smaller because they're not the centerpiece. So to find x hat, first we have to compute two things. We have to compute A transpose B, and we have to compute A transpose A. So let's first start with A transpose B. We have 1, 1, 1, 0, 1, 2 times 6, 0, 0. We are getting a vector with two components. So the first row times 6, 0, 0 is just 6. The second row times 6, 0, 0 is just 0. So that's A transpose B. Now A transpose A is equal to 1, 1, 1, 0, 1, 2 times 1, 1, 1, 0, 1, 2, and that equals, so we have a 1, 1, 1 times 1, 1, 1, and that's simply 3. Then we have again a 3, and again a 3, and then we have 1 plus 4, which is a 5. So this is A transpose A. We have two ways of solving this system. One way is to find the inverse. Another way is to just solve. So this is only when we're trying to find x hat. And that's enough for to find the two answers to x hat and the projection P. But we will need the inverse to find the projection matrix. For now, let's just focus on the first two parts. We'll worry about the projection matrix in a minute because I want to show you how you can avoid computing inverse matrices. On a 2x2, next week we will learn a formula, how to compute the inverse of a 2x2 matrix. But in general, finding matrices is not an efficient thing to do. So it's actually far more efficient to just solve the system. Okay, so we have 3, 3, 3, 5 times x hat. So x hat will have x1 hat and x2 hat, two components, equals 6, 0. So you see, I can find this by simply applying Gaussian elimination. I don't have to find the inverse. And that's exactly what I'll do here because it's always easier than finding inverses. Although for a 2x2 matrix, both are fairly easy. So I can do 3, 3, 6, 3, 5, 0. I need to reduce that system. Here is my pivot. I'm reducing underneath. I have R2 minus R1 into R2. And I get 3, 3, 0, 2, 6, negative 6. From here, I can straight away compute what I have. So I have x1, or rather x2 first. From the second row, I have 2x2 equals negative 6, which means x2 equals negative 3. That's x2 hat. And then applying that in the first row where I have 3x1 plus 3x2 equals 6. So I guess I'll write that. I could divide everything by 3 and replace that 6 with a 2. That makes things a lot easier. And now I have x1 minus 3 equals 2, which means x1 hat is a 5. So the answer to finding x hat is 5, negative 3. Now to find the projection little p, p is A times x hat, so I just have to multiply the matrix A, 1, 1, 1, 0, 1, 2, times x hat. And I'm going to get a vector with 3 components because remember, p is supposed to replace b. So p and b are in 3 space, but x hat is not. So we have a 5 here. 5 minus 3 is a 2. 5 minus 6 is a negative 1. So this is the projection P. Now to find the projection matrix, I do have to find the inverse of the matrix A transpose A. So I'll do that here. Maybe I'll start with the formula. P equals A times A transpose A inverse times A transpose. So A transpose A equals 3, 3, 3, 5. To find the inverse, so far we've only studied Gauss-Jordan. So I'll use that. Once we study determinants, you will have another way of finding, for a 2x2 matrix, you'll actually have a formula. But for now, we'll use Gauss-Jordan. So I'll reduce there and have R2 minus R1 into R2. We already took that step on the previous page. So we have 3, 3, 2, and here we have 1, negative 1, 1. Now I will take, I suppose it's easier at this point to divide by the pivots because I have a 3 and a 2, and then there is a 3 again in the first row. So what I'll do here is I'll say 1/3 R1 into R1 and 1/2 R2 into R2. We have to deal with fractions at some point no matter what, but it will make the calculations on the left-hand side a little easier. So here we have a 1/3, here we have a negative 1/2 and a 1/2. And the final step is to eliminate with this pivot above. The operation is easy. The operation is R1 minus R2 into R1, and we will have to deal with some fractions. So here we have the identity on the left-hand side. On the right-hand side, I will have a 1/3 plus a 1/2 actually. So that's 5/6. One of the first fraction problems I gave to my son. He knows it by heart. Okay, the next one is 0 minus a 1/2. So that's very easy. Negative 1/2, negative 1/2, 1/2. So actually that was quite easy to do. Only one fraction really to deal with. I could represent this. So A transpose A inverse is that matrix, which I'm going to write in the following way. I'm going to take a 1/6. I'm going to factor out a 1/6 out. Then this will be a 5. This will be a negative 3, negative 3, and a 3. All right. So we have A transpose A inverse. And now to find P, I have to multiply all the matrices. So A was 1, 1, 1, 0, 1, 2. 1, 1, 1, 0, 1, 2 times a 1/6. I can take that 1/6 here on the left. Then I have 5, negative 3, negative 3, 3 times the transpose of A, which is 1, 1, 1, 0, 1, 2. You can carry out this multiplication however you like. I'm going to multiply these two matrices. So by however you like, I mean you could either multiply this matrix by this matrix and then multiply the product, or you could multiply these two and then multiply that product times that matrix. You cannot rearrange the matrices, so you have to respect the order. Okay, I have a 1/6 times 1, 1, 1, 0, 1, 2 times, the matrix is going to have to be, again, a 2 by 3 matrix. So we have a 5 here, then 5 minus 3 is a 2, 5 minus 6 is a negative 1. Then we have negative 3, negative 3 plus 3 is a 0, negative 3 plus 6 is a 3. That equals 1/6 times, now we're going to get a 3 by 3 matrix. However, that matrix is going to have rank 2. 1, 0 times 5, negative 3 is a 5. 1, 0 times 2, 0 is a 2. Then we have negative 1. Then we have 5 minus 3. Then we have a 2. And this matrix better be symmetric. Negative 1 plus 3 is a 2. 5 minus 6 is a negative 1. Then we have a 2. And then we have negative 1 plus 6, which is a 5. So we get a symmetric matrix. You don't have to ever multiply this 6 in. This is a much nicer form. Just leave it at that. So this projection matrix applied onto any vector B will give us the projection onto the column space of A. Now, unless you're asked to find the projection matrix, I really don't see why you would have to be bothered with finding the inverse. It does take a few steps even for a 2 by 2 matrix. We actually took a lot less space to just find what x hat and the projection P were in here. You could have very well computed A transpose A inverse times A transpose, multiply that by B. So we already have that matrix, right? This over here is, well, with the sixth. So this is A transpose A inverse times A transpose times the sixth. So I have to include that sixth here, right? So you compute that matrix. So 1/6 of this is A transpose A inverse A transpose. You could multiply that matrix by B to obtain x hat. You can check that that's it really so. Then from there, again, you have to multiply by A, or you could first find the projection matrix, multiply by B to get little p, right? So if you take that matrix P, that's exactly this thing, you multiply by B, and you're going to get little p. So more than one way to do this, but unless you're asked to find the projection matrix, I do advise against all these multiplications. They take way too much time. They're unnecessary. We solved 2 problems just with this space, right? It didn't take that long. All right, now I promised one final thing to do. So in our proof of the system here, we used in our proof of the formulas for projections, we used one fact which I have not proven, and that is the following. A transpose A is invertible if and only if A has linearly independent columns. So we'll prove this, and with that we'll end for today. So what is the proof of this statement? No matter what A is, so A is by assumption some rectangular matrix, right? So A is an m by n matrix. Could be square matrix, but we don't know, so we are assuming it's just a general rectangular matrix. And but you see, A transpose A is going to be an n by n matrix. So the way we're going to prove this is really, or we can restate the statement in the following way. So because A transpose A is a square matrix, no matter what A is, to say that A transpose A is invertible is to say that its null space is just 0. So the null space of A transpose A is 0 if and only if, so when I want to say if and only if, I write if with double F. Now, what about A has linearly independent columns? Well, what is in the null space of A? The null space of A consists of combinations, non-trivial combinations of the columns that give a 0. Well, if the columns are linearly independent, the only way to get a 0 with a combination of them is the trivial one. So this whole statement translates into the null space of A transpose A is 0 if and only if the null space of A is 0, right? So the statements are equivalent. I can talk about invertibility and linear independence, or I can talk about null spaces. They mean the same thing. Now, if and only if is, so the mathematical symbol is this double-sided arrow. And the reason for that is that we are proving two things. We need to show that if the null space of A transpose A is 0, then the null space of A must also be 0. So that's step number 1. Step number 2 is if we know that the null space of A is 0, then it must be the case that the null space of A transpose A is 0. So this is a two-sided, or it's two-way street. If I assume this, then I know that. If I know this, then I know that. So it's in both directions. And proofs like this need to be done in two ways. So step number 1, if the null space of A is 0, so this is our assumption, we need to show that the null space of A transpose A is also 0. Okay, so how do I show that the null space is 0? Well, let's take a vector in the null space. So take x in the null space of A transpose A. What does that mean? Well, it means that A transpose A times x must be 0. Okay, I know this. I know that A transpose A is 0. That's what it means to take a vector in the null space of A transpose A. Okay. So what can I do from here? Well, it's a very simple trick, actually. And it really is a trick, so you have to know how to do this. I'm going to multiply this equation by x transpose. I'm going to write x transpose A transpose A x is x transpose times 0. But x transpose times 0 is just 0. So when you have an equation equal to 0, you could very well multiply it by anything, as long as the dimensions or the sizes match. Okay, why did I do this? Well, you see, x transpose A transpose is the transpose of AX, right? So what I have is AX transpose times AX is 0. Now think of AX as some vector. This is a vector, I don't know, y, for example, or b, or t, or k. It doesn't matter. It's some vector. It's like A transpose A. Well, what's A transpose A? This is the norm of the vector A, the length, squared. That's actually how we define length. So what we have here is that the length of the vector AX squared must be 0. Well, if the square of the length is 0, that really just means that AX is 0. The length of AX is 0. Well, the only way for a vector to have length 0 is for that vector to be the 0 vector. So if you can show that the length of a vector is 0, then you know that the vector is also 0. So what have we shown? We have shown that if x is in the null space of A transpose A, then x must also be in the null space of A. This AX equals 0 means that x is in the null space of A. That's exactly the definition of the null space. But what did we assume? We assumed that the null space of A is just 0. There is nothing other than the 0 vector. So if this x is in the set null space of A, and the null space of A is just 0, it means that this vector x must be the 0 vector. So we showed that x is the 0 vector. Okay, how is this useful? Well, we took an arbitrary vector in the null space of A transpose A, and we showed that that arbitrary vector is just 0. So we have that the null space of A transpose A is 0. In fact, with this proof, we proved something stronger than the null space of A transpose A is 0 if and only if the null space of A is 0. What we showed with this proof, in fact, is that the null space of A transpose A, so this part 1 over here, what we did was we took a vector in the null space of A transpose A, and we showed that that vector is in the null space of A. In other words, this set, or this space, is a subspace of this space. So the null space of A transpose A is inside the null space of A. Now, just because we assumed that the null space of A is 0, it turned out that they're equal, but in this particular case. But in fact, we show that this space is inside the null space of A. Part 2 of the proof will show the opposite. And in fact, we will have proven a much stronger statement which says that the null space of A transpose A is the same as the null space of A. That is a much stronger statement, which we're proving sort of along the way. Okay, part 2 of the proof. If the null space of A transpose A is 0, so now we are assuming this to be true, we're not proving it, we show that the null space of A is also 0. Okay, how are we going to do that? Well, to show that the null space of A is 0, I better take a vector in that null space. So I'm going to take a vector in that null space and check that it's the 0 vector. So a vector in the null space of A satisfies the equation AX equals 0. Okay. Now, I'm going to multiply both sides of this equation by A transpose. I'm trying to get to A transpose. So I have A transpose AX is also 0. Now, by putting parentheses around A transpose A, what do I have? I have that X is in the null space of A transpose A. So this came from the fact that we took an X in the null space of A. And now this equation says that X is in the null space of A transpose A. But the null space of A transpose A only contains the 0 vector. So this says that X must be the 0 vector. And therefore we are done with the proof. So in summary, the stronger statement here is that the null space of A transpose A equals the null space of A. The same proof without going all the way to the fact that X equals 0. So I'm not assuming here, this is a stronger statement because I'm not assuming that the columns of A are linearly independent. That no longer matters. I'm not assuming that either null space is just 0. What I'm saying is that one set is a subset of the other. So you can make all of these arguments minus X equals 0. So all the way here, because we took an AX in the null space of A transpose A, and we showed that X must be in the null space of A, we're saying this is inside this. Now in part 2, we took an X in the null space of A, and we showed that it must be in the null space of A transpose A. So we showed that this is a subset here. Well, when you have two sets, if the set S is inside the set T, and the set T is inside the set S, then it must be the case that S and T are the same. So that's exactly the conclusion, and we have proven this even though we were trying to prove this equals 0. The 0 was less important. All right, that is all for today.